Okay, so today we're going to start talking about energy, which will be a concept that will underlie the rest of the semester and really the rest of your study of physics. Of course, that brings up the question, what exactly is energy? Unfortunately, there's no simple, straightforward answer. It is the ability to, it has something to do with making things move or warm up. I sometimes like to say it's the ability to do damage. Sometimes it's called the ability to do work, but we will later learn that work is basically a transfer of energy, so it's a bit circular. But something that's able to hurt something that's able to cause damage, generally has more energy. Something that's able to make something move or warm up generally has energy. And we're going to learn a concept known as the conservation of energy, which basically states that energy can be moved from one place to another and changed in form, but that its total amount always stays the same. It's kind of like this apple here. It can be cut into apple slices or pureed into apple sauce, but the total amount of apple there stays constant. So let's take a look at the things we want to know by the end of this chapter. You should be able to explain the concepts of work and kinetic energy, as well as the relationship between them, provide example situations in which these ideas are most useful. You should be able to describe how the spring force is different from constant forces, and how the spring force is related to the spring constant and displacement of the end of the spring from equilibrium, and apply that in quantitative situations. Calculate the work done by one or more forces in multiple dimensions, and evaluate the sign. Apply the work-energy theorem to solve quantitative problems. Use the dot product to calculate work. Explain the concept of power and apply this concept in quantitative situations. The origins of energy are very similar to the origins of momentum. Remember, with momentum, we started from the equation that the net force was equal to mass times acceleration. And then we integrated both sides of this equation. Alright, this side we gave a name. We said it was the impulse, J. And this side we could actually integrate. M was constant, A was equal to dv dt. So if we integrated it from one time to another, we got mass times v final, or v at time 2, minus mass times v at time 1. And we called this quantity, mv, the momentum. Okay, so that's what we did with momentum. And we found that it was very good in figuring out what happened to an object after a force acted for a certain time. We've got a force integrated with respect to time, so naturally it would work for a force over a certain time.